Nice to meet you. I'm Prof.Joun, working for Gyeongsang in Korea. The topic of this lecture is concept of FEM for partial differentiations with boundary conditions. It is aimed just to introduce the concept by expanding the conceptual knowledge of ordinary differentiations taught in the previous lecture. Some more detailed contents can be found from this reference, which is targeted at introducing final method coupled with mathematics and solid mechanics. First, let me break the basic concept of FEM in engineering with emphasis on metal forming. Natural phenomena in mechanics or electromagnetics is formulated by boundary value problems, generally involving partial differentiations and initial and/or boundary conditions. It is noted that even professors majored in mathematics cannot solve a practical problem occurring in engineering by hand calculation. It is of course very lucky because we don't have to stand online waiting for the answers of our engineering problems in front of their office. However, after all, we have to arrive at mathematical station to solve them. 111 years ago, a Swiss theoretical physicist Ritz developed an approximation method of boundary problem based on variational approach. 6 years later, after Ritz's contribution, Galukin, a Russian engineering mathematician, presented the Galukin approach. These two approximation methods developed 2 generations before the birth of practical and powerful computer has built the theoretical backgrounds of the final method. However, their approaches were impractical in those days because of complicated integration and difficulty in solving linear equations and in preparing trial functions satisfying essential boundary conditions, especially when they are applied to 2D or 3D problems. These problems could become solvable by computer and final element techniques. Computer is characterized by fast calculation and faithfulness, while final element techniques are by final element discretization and interpolation, that is, finite element approximation. With the assistance of these 2 factors, the approximation method became to bloom in 1960s to be applied to solid mechanics and fluid mechanics. In metal forming simulation, we are capable of predicting everything related to mechanical, thermal, metallurgical changes during metal forming based on the computerized analysis method with proper mathematical models of the process. Now, let me define the problem of metal forming simulation. There are 3 laws of nature involving laws of mass, momentum, and energy conservations. They are formulated by governing equations called equation of continuity, equation of equilibrium when the acceleration term is neglected, and equation of conduction, respectively. Through finite element approximation, they are transformed into a set of linear or nonlinear equations of which unknowns include only fundamentals such as displacement or its increment, velocity, temperature rate, hydrostatic pressure, depending on the formulation. The other variables, including stress, strain rate, formula load, temperature, heat flux, and the like, can be calculated from the fundamental variables in finite element analysis. The finite element analysis code excluding the pre- and post-processors is called finite element solver. So the commercialized finite element analysis software is composed of 3 modules, that is, preprocessor, FEM solver, and postprocessor. The preprocessor is usually connected with CAD systems and supports users to prepare the final analysis models. The manifolding simulation problem can be coupled with methodological analysis problem, and the analysis function can be also linked with design system to optimize the manifolding processes in terms of formula, manufacturing, or product quality. And final element code can be linked to other softwares to get some initial or changing state variables or to splice them for the other softwares. Recently, manifolding softwares are being tried to diagnose the machine problem and foretell the die or machine lives in the smart manufacturing system. In other words, it is going to play a role of the brain of human being gradually. Now, let us expound the concept well established previously from a one-dimensional problem as summarized here to the problem on the two-dimensional plane. You know, a 2D problem is mathematically the same with a 3D problem. The differentiation on the two-dimensional plane corresponding to that on a line segment is Poisson's equation, as formulated here by second-order partial differentiation. We have some simple but typical boundary conditions, that is, this essential boundary condition and this natural boundary condition. This Poisson's equation is sometimes utilized to formulate steady-state heat conduction problem, seepage problem, lubrication problem, and so on. Its corresponding Bayes principle is formulated like this. The last term of this functional is owing to the natural boundary condition. You can see at a glance that the patterns of these two functionals are almost the same with each other, excluding this natural boundary condition term. Anyway, it is very interesting that the natural boundary condition disappeared with this evidence left. When we start from this variation principle, we will arrive at the variation approach to finite element method. The weak form of the boundary value problem can be formulated like this. You can see that the natural boundary condition was also embedded into the integral equation, as can be seen here. When we start from this weak form, we will arrive at the weighted residual approach to finite element method. The solution domain on the plane is discretized into quadrilateral and or triangular elements, as can be seen here. We are going to use these finite elements with emphasis on node J to explain the interpolation function on the two-dimensional plane. Let's first configure a bilinear interpolation function NJX, y defined at node J. The function has non-zero value only over the elements which are defined by the node J. You can imagine that the interpolation function Nj changes with nodal values of the node J. Similarly to one-dimensional case, the interpolation function value Njx, y should be unity at that node and 0 at all the other nodes. The function value along the edges of elements, for example, for edges in this case, varies linearly with the distance. Therefore, all subfunctions defined along the edges should be straight. It is also interesting to note that the subfunction should be straight, which is defined on any line segment connecting two matching points on the opposite sides of a quadrilateral, which have the same normalized length along the edges. For example, the normalized distances at this and these two middle points are all 0.5. The line segment connecting these 2 points with the same normalized distance should thus be the subfunction, like this. All the other lines in these figures were drawn in that way. Now you can imagine the configuration of the entire interpolation function nj from these figures showing the function in various directions. The interpolation function defined over a triangular element construct a plane as can be seen in this figure. Please refer to any reference to be advised for the simple interpolation function defined over a triangle element. Now, let's check the trig function and weighting function. Because a known function is scalar valued, we have to define one unknown nodal value and one arbitrary nodal weighting constant at the node j, that is phi j and wj. Then we can approximate the unknown function and weighting function as linear combinations of interpolation functions with their corresponding nodal values as stated here and here respectively. For integration over a quadrilateral element, it should be mapped into psi eta natural domain, a scale defined by 4 natural coordinates of 1, minus 1, 1, 1, minus 1, 1, minus 1, minus 1, denoted by local node numbers 1, 2, 3, and 4 in counterclockwise direction. It should be emphasized that we have to map each quadrilateral element from actual solution domain to natural domain defined by a scale like this to calculate definite integrals in a numerical way. In the mapping, one-to-one correspondence between two nodes in actual and natural domain should be satisfied. However, during metaforming simulation, a finite element can be too distorted to meet the essential requirements, which is one of characteristics of foraging simulation. In this case, remeshing is inevitable, which should be carefully treated because it causes artificial change of static variables as well as deformed shape of material. Now, let's derive final equation from Clarkin approximation using these approximations. Substituting this equation into weak form, we obtain this equation, an identity equation with respect to the nodal weighting constant. Eventually, we obtain a set of these finite equations just before applying the essential bound conditions. In this finite element equation, Kij and Fi are stiffness matrix and force vector respectively, defined by these equations. So it is interesting to note that they are using the same terminology of stiffness matrix even in fluid mechanics or thermal engineering. Applying the bound conditions, we get this final element equation where the bar on an index is used for the nodes on the essential bound condition. Now, let's study on finite element formulation and approximation of linear elastic problem of an isotropic material defined conceptually by this figure. The solution domain is composed of balloon denoted by V and its surface denoted by S. The surface S is divided into essential and natural boundaries denoted by SUI and STI respectively. Its associated boundary value problem is formulated by this equation of equilibrium, Hooke's law for an isotropic material, and strain displacement relationship. The vector functions with bars represent the given functions. This formulation is the virtual principle, the necessary condition of the total potential theorem for 3D elastic body. Replacing virtual displacement by weighting function, we can directly obtain the weak form corresponding to the boundary value problem formulated by Newtonian mechanics. Of course, we can derive this weak form directly from this boundary value problem in the formal way we did for the one-dimensional case. Please refer to any kind of textbook for some more detail about it. Now we are going to enter a little complicated space where our lifelong friends of values are waiting for us. This is the vector of nodal displacements. Some of them are knowns and the others are unknowns. Of course, three nodal displacements, U1, U2, and U3 for each node are defined for x1, x2, and x3 components respectively. In the same way, we define the nodal weighting constant as formulated by this equation. We can approximate the vector functions of ui and omega I by these equations, where the interpolation matrix NIL is defined by this relation. That is, the component NIL is defined by interpolation function defined at node L, which has unity function value only at node L. When we define stress and strain component vectors sigma I and epsilon I like these relations, the Hooke's law can be rewritten like this. Dij is defined here and called elastic matrix. From strain displacement relationship, we can link the strain component vector we defined into the nodal displacement as formulated by this equation. Here, BIL is called strain displacement matrix. We can also express the stress component vector in terms of nodal displacement like this. The diffusion term, the double inner product of two tensors, that is inner product of stress component vector and weighting function component vector beta I, is expressed in terms of nodal displacement and weighting constant like this. Here, the vector beta I is defined in the same way as the strain component vector. Beta I can be formulated as function of nodal weighting constant with the strain displacement matrix. Now, plugging this approximated diffusion term and weighting function into the weak form, we obtain this identity equation with respect to Wi. After all, we obtain this finite element equation for elastic deformation of the linear isotropic material before imposing essential boundary conditions. Of course, Kij and Fi are called stiffness matrix and force vector, respectively. We already studied the necessity of remassing for one-to-one correspondence in the mapping process between actual and natural domains when a finite element is too distorted to satisfy the requirements on the one-to-one correspondence. This slide shows a typical example of process where remassing is important. In this forming process, remassing has great influence on the prediction. Remassing inevitably causes not only artificial change of solution domain, but also smoothing of state variables. Thus, remassing should be carefully dealt with. Of course, mass density is also important for solution accuracy. In the case of piercing process, the shearing region should be finely meshed, while quite rough fine elements outside of the major deforming region has negligible influence on the accuracy of predictions. We call our metalforming simulation as intelligent metalforming simulation because we employ optimized fine element mesh systems regardless of user's request. In this slide, I'm going to show you some excellent fine element mesh systems, which can give you some insight on the intelligent metalforming simulation in terms of accuracy and reliability. As I mentioned, some problems are caused by remeshing, leading to inaccuracy. The number of remeshings should thus be minimized when remeshing should be done because of severely distorted element or mismatch at the interface between material and dies or tools. The boundary conditions should be kept. Yeah, it is because we are solving boundary barrier problems. Obvious solutions depend on the boundary conditions. In this figure, blue color means free surface. In this simulation, we maintain higher mass density along the boundary of contact interface as can be seen in the isolated region. You can see how we treat the mass density along the peripheral of the pre-surface while it disappears. To reduce the number of remeshings, we'd better not use too small elements because they are exposed to becoming degenerate elements due to locally severe distortion, which leads to frequent remeshing. To the contrary, we have to use some skillful and special function to describe the characteristic edges, curves, or surfaces of material for higher accuracy, with properly limited number of elements. These examples show such model cases of good math system for metalforming simulation. It should be noted again that higher number of elements in metalforming simulation, especially densified around the major deforming region, does not guarantee so much high accuracy because of frequent remeshing. This slide compares the predictions with experiments. The left two compare predicted rainfall lines with experiments of asymmetric hot forging processes. This is a comparison of asymmetric cold forging in terms of deformed shape. In this case, the dimensions of the deformed forging are very important. Anyway, it can be concluded that the predictions are almost the same with the experiments. This is for comparison of predictions with experiments of counter-blow hammer forging of a crankshaft applied to medium-sized ship engine, sometimes used for power generator. So it is concluded that the predicted shape is very close to the experiment, which can contribute to removing the costly and time-consuming process and trial